RCs. Everybody, any answer for part A? So for part A, it's asking about how many atoms are associated with the cell. So means like how many atoms are in the cell, within the cell. It's the same thing. So we just have to count. So we have two atoms at top and bottom edges, which are half of them are in the cell. So basically these two make the one total atom. Plus we have three atoms at the center, which are totally located in the center. So far we have counted 4 atoms, right? So I guess these atoms have their monomers are a problem. So if you just imagine, this is an example. So each atom is sharing one fixed other in this cell. And you have 6 atoms at each edge or at each surface. So basically, in the top edge, if you just consider these 6 corner atoms, all of them together make one total atom, one complete atom. Same thing for the atoms at the bottom surface. So in total, we have 6 atoms associated, 6 total atoms associated with this unit cell. Right? So that was part A. How about part B, the coordination? And the coordination number is the number of neighbor atoms or closest atoms. Yeah, that's right. So if you consider, for example, this atom here, you have 6 atoms in the same plane as this atom. Plus you have 3 at the lower or bottom surface, and also you have 3 at the bottom surface, right? So in total means 12 atoms which are closest to that atom. It is same for the other atoms as well. Does that make sense? We want to count how many atoms are neighbor to this one atom. So you have 6 here, 3 at the bottom, and since it is repeatable, you have 3 at the top. Okay. And the last part is asking about APF. So for the APF, again, we have to do the same thing. We have to find the volume of the unit cells, and also we have to find the relation between the volume dimensions. Here we have 2 dimensions. We have C as the height of the total structure, and we have A as the edge of these pixels. So we have to find the relation between A and C and R. And the total volume of the total structure is going to be C times the area of these surfaces, right? So let's switch to it's always, we assume it's 1.633, right? So that makes it much easier. And to find the relation between A and R. So if you look at just one edge, so you have two atoms. So we assume this, we label this edge as A, right? And you have two atoms touching each other. So A is equal to 2R. Does that make sense? Because this is just one edge. If you just consider this part here, in the actual structure, these two atoms are touching each other. Right? So, and so this distance is going to be R, which is equal to half of the A, and this is also R, radius of one atom, which makes half of this distance, A over 2. Yeah, okay. So this one is better actually because in this, in this image, the atoms are not actually touching each other, but the actual structure is something like this. You can see the atoms are close packed together, so they're actually touching, and this distance here is A, which is equal to 2R. Since this one is very hard to draw, it's not that good. So does it make sense? Does anyone have any questions so far? So knowing this, so we already know the relation between C and A, and also the relation between A and R, which is A equals to 2 times R. We just have to find the area of the hexagon or other surface, top surface. So just takes a little bit of geometry, but when you have a hexagon, I'm not go over all these equations, but just to show you how to drive this relation. So first, you want to calculate the BC, which is the height of a triangle, right? So the BC, so you have a 30 degrees angle here. The BC is A times cosine 30, which in this case, A is 2R. Yeah, so BC is A times, which is the height of the triangle, is A times cosine 30, and we know A is equal to 2R, so we can just substitute 2R, so we get 2R times cosine 30. So if we want to calculate, so we already know like the height of this triangle here. If we want to calculate the area of this triangle, you get the height times AC, which is A, or equal to 2R over 2. And in total, we have 6 triangles. So that's what we get at the end. That's the total area. So CD is just A here, replaced by 2R. And the BC is just the height. So the area is going to be, this is like total area. And when you times it, you just have to multiply it by C to get the total volume. And we already know the C is equal to 1.633 times A, which is 2R. And this is the total volume based on R. After you substitute R, that's what you get at the end. That was really hard. Just imagine the shape of the cubic structure. So So, any questions? Well, it's a good idea to remember APF. We also have it, just show you how we drive this APF, but you have it in your slides. We have APF and the ratio between C and A. It's good to memorize this one.
So basically this question is asking, what is the difference between atomic structure and crystal structure? We can go through this one really quick, just because it's not too bad. I actually want to get into explaining the math for inside of this one, because there's, I forget which question it was, but that one was talking about the diamond structure, like the actual atoms in there, so that was a little difficult. So this one, what is the difference between atomic structure and crystal structure? You guys should be selecting the answer that reads atomic structure relates to the number of protons and neutrons in the nucleus of an atom, as well as the number and probability distributions of the constituent electrons. So now if we move on to, I think number 2, where we have some more math. I think you guys did pretty well on this one. But we'll go ahead and go over the math on this one. So if the atomic radius of aluminum is 0.143, calculate the volume of the unit cell. So this is kind of what we've been going over earlier today. So again, this is so gold and aluminum should be FCC. So you should be using the VC formula, which is so basically the FCC formula that we went over earlier today, which is VC is equal to 16R cubed times the square root of 2, or better yet, I think we wrote it a little bit differently. I'll put it back here on the screen. So it's this guy here where my mouse is at. But if you were to simplify that out, it would be 16 multiplied by r cubed multiplied by the square root of 2, and then from there you would get your answer. So basically you're using this guy here to help solve for that question. So not too bad, we kind of already know that one today. So we're going to go into, oh yeah, do you have a question?
I just saw it.
sorry. Yeah, it's this one. So if you simplify it, you'll get the formula that I was just mentioning earlier. But let's just try and jump into a new one. So next time. I'm wondering this is about the same. So this is calculating theoretical density. From the amount of people that already answered so far the homework, it's not bad. So there's an equation, a density equation that you guys would plug values into, and then again for I believe this is niobium would be VCC structure. So the VC that we saw for in earlier today for the VCC structure, if you guys remember, we'll be putting that into your density equation. So here again is the volume of the cubic structure that I'm talking about, that we're gonna use for this problem in particular. But, for that problem, they want to look at the density of, I think it was niobium was. So essentially it's this formula here. So density is equal to NA over VC and A. And then we know what the VC is. That is for Q3 cubed and your N is basically your atoms per unit cell. In this case, it would be 2 atoms per unit cell. The A is going to be finished atoms per unit cell. Yeah, so then your A is going to be the atomic weights, which is if you put that into parents or business. So basically this A is going to be your atomic weight. And then we see we know what that is, and then our NA is supposed to be Avogadro's number. Here, and it's just 2 atoms per unit cell, or atoms per unit cell is your N value. And then it's the sulfur density, so that one's it's not too bad. So we're intentionally not putting numbers in because the numbers that we're seeing on our side, we don't want you guys to get confused like on your side. But at least we want to show you guys like what you should be looking at. So this is gonna be like your main formula. This is like the breakdown for this guy. So basically, once you identify what your values for your VC, once you figure out N, your atomic weight, and Avogadro's number, you go ahead and plug it in and find density. And for the people that already started homework already, they didn't have too much trouble with this one. So we didn't spend too much time on this one. I think in your homework, there's some unit vector ones that I think you guys will want to know about. Again, I believe it's still the same. And so for this one as well, it's kind of the same thing. Use that same density formula, figure out what your VC, figure out what your A is, which is your atomic weight, so on and so forth, and you go ahead and plug it in, and you should end up with your density. Number 5. They mentioned indium has a tetragonal unit cell. The AC last parameters are given right there as 0.459 and 0.459, and for C it's 0.495. They want you to figure out the atomic packing factor and atomic radius, determine the number of atoms in each unit cell if the atomic packing factor is 0.693 and the atomic radius is 0.625. And then they give you the atomic weight in part B, and they want you to find the density. So part B again is what we've already done in the last two questions. I believe part A might be a little new. Yeah, so the part A is just your APF formula. So really quickly, I'll show you guys that. So that's you guys can see that. So your atomic packing factor equation is just VS over VC, which is just n times 4/3 pi times the radius cubed. And then again, your VC is your volume for the cubic cell, which is just a squared multiplied by c. And then, yeah, so for this one, you need to rearrange this. So this is what you're actually looking at.
We can't do that.
Oh, sorry. Okay, so this is what we're gonna end up with here. And so now we have to rearrange this so that we get n. So you have n is equal to the APS number, right? And then we multiply that by a squared c divided by 4/3 by r cubed. And then from here, you'll end up with your atoms per unit cell. And that would be basically your answer for that one. And then part B is just the density one. So again, this equation should be in your slides and also in your text as well, so it's not too bad to manipulate. You just have to learn to find it and definitely practice. And the practice questions that was over today too, we're gonna upload those to Canvas so you guys can see it. Okay, so then there's one, this one. Yeah, this one, even I looked at it, I was like, whoa, what's happening? So we'll go over this one as best as we can. So the question is reading, select the point indices of all the atoms associated with the diamond cube unit cell. And then from here you would select all the ones that pertain to the answer. So and I guess to help you guys out too, they gave you there's a hyperlink there that takes you to that section in the note or in the textbook to the unit cell itself. And so
it's different in Ireland or not, but it might be different. But in general, it's simple. Usually, what we do is we take this corner here as the our origin. So this would be the x-axis, this is y, and this is z, right? So it's asking about the coordination of each atom. So for example, if you take, if that's the origin, and this is, for example, the atom you want to know its coordination, it's gonna be 1, 0, 0, right? Because it's on the x-axis, and it has just one unit. This is going to be on 1. So basically what we are doing is we are doing something like this. So it's going to be x, y, and z. So, and we can project the unit cell on these axes. Something like this. So we have different atoms in this unit cell. For example, the atom sitting here at this corner is going to have the coordination of 1, 0, and 0, right? So you can do the same for the other atoms as well. So this structure has a lot of atoms. You have to check the coordination of each atom and select all the coordinations that are present at this structure. Does it make sense? Anyone has any question about this? Yeah, you have to see it. You have to check all the coordinations that actually related corresponding to one of these atoms. So for example, like this is the origin, so this is 0, 0, 0. And this is the x-axis, so it's going to be 1, 0, 0, because the y and z for this atom, this particular atom is going to be 0, right? But you can move, you can check for the other atoms. For example, for this one, which I believe is in the center of that face, so it has the coordination, look, the y coordination for this one is going to be 0, right? Because it's in the xz surface. So you have to find the z and x coordinations for this one. Since it is, I believe it's in the center, so it's going to be 1 over 2, 0.5. This is coordination. We are trying to get integers, so it's going to be 2, 0, 2. That's how we normalize it. We don't want to get like fractions. So when we have, so writing the coordination for this one is going to be 1 over 2, 0, 1 over 2. Then we multiply everything by 2 to get integers, right? So basically that's it. You have to check all those points, coordinations, and check if they are related to any atoms in this structure or not.
this one is one of the more straightforward ones that you guys had. And it's actually asking which one is FCC. And again, you can get that from your slides and stuff too. It's the face-centered cubic structure basically, which is, see if I can select these. So here, for example, this is BCC. This is not what they're asking for. This one also kind of like BCC. That's what it reminds me of. And so FCC, the one that they're asking for, should be. So the orthorhombic part is the part that you have to be careful of. So that's the tricky part of this question. So face-centered cubic or face-centered should give away to you that it will look like this one, but because of the orthorhombic part that they add in there, it's not going to be this guy. Because if you look at this one, it's a square. When you are looking at the orthorhombic, face-centered orthorhombic crystal structure, it's going to be this bigger here. I guess you could call it a rectangular prism. So you can see that you have atoms here in the face, and all your atoms at the edge. But it's taller, it has a height C to it, versus the cubic FCC, which only has A on each side. Which means that it has equal length. Unit cell length on each side versus this guy. So for this one, this would be the one that you would select because that's the orthorhombic FCC structure. So not too bad. For this one, so in the table below, they want you to list the point coordinates of the atoms found in the FCC that are labeled with the following numbers, 5, 6, and 12. Well, in this one, they want you to find 5, 6, and 12, at least on my side. So this guy down here, this guy here, and then 12 is there in the corner. So, and then here they give you like the X, Y, Z to actually find it. So we can convert this one. So quickly, I will to draw over here, but I'm not sure how to draw it. That's a little confusing. And this one's supposed to be on this face. Then these guys here are supposed to be on the back one. So maybe I can do this so that it looks more. Okay, so I believe in that one they wanted us to find, or I should say, let's try and solve it in general.
this is basically the same thing as the previous one. Well, I'm gonna show you like from the actual, because it's easier to see. So if this is, so this is the actual structure. So for example, we're asked to find the coordinates of a specific atoms. Let's say we want the coordinates of atoms number 4, right? So if the number 1 is the origin, so it's like 0, 0, 0, what would be the coordinates of number 4? Exactly, 0, 1, 0. So it's the same thing, so it's asked, for example, for number 5, I guess, so it's gonna be, so you have 0 for the z-axis, because it's in the xy plane, and since it is center, we have FCC structure. The center, so you would have, again, half for each x and y coordinates. But we don't want to have like fractions or floating numbers, so we have to normalize it to integers. So we get 2, 2, 0, for example, number 5. Well, number 5 in your end might be different, but that's how we generally do it, right? Just assume this is like the normal Cartesian 3D coordination system, and you have to find the coordination of each point. That's how it's done. If you look at the textbook, it's a little bit, it has a different method to find the coordination, which is based on vector, and it's basically the same thing, which just makes it amazing. It's good to see. So it's asking determine indices for direction shown in the following case. So it's about direction. It's almost the same as the point, but it's about the direction of point coordinates. So let's see. So for example, part A is asking for what is the x coordinate for the vector tail x1. Well, it is about direction A. So direction A is the top vector at the top face. If you see it, that's green vector. This one, and you can see the question and the vector, but for some reason I can't do it. So, but it's pretty, well, it's exactly the same. So it's asking for the coordinate of the tail of that vector. Well, the tail is basically where the vector starts. For example, for vector D, which is the red one, the tail is going to be this point. The head is going to be pointed, right? So exactly the same thing. You just have to find the coordinate of the starting point or the tail point for the A, or its And it makes it easier because it's only asking for the x coordinate of that point. So in this case, for example, the x coordinate is going to be 1, right? Because it's starting from here. If you project that point on the x-axis, you get 1. And you do the same thing for the other points. It's asking, for example, for the head of the vector is here, and it's asking about only the x, only the x coordinate of this point, which is going to be 0. And we do the same thing for other points for other axes. Is this clear? And it's basically the same thing. Question number 10. This one is more tricky. Actually, I can see some students have a little bit of problem with these questions. So, it's the same idea, but since we have hexagonal structure, it's going to be a little bit different. So we have 4 different axes here, so we're gonna have 4 indices. That makes it different, and so then I have to. This is the hexagonal structure. So what we do here is first we find this capital U, V, W, and that's how we transform these numbers to the actual indices. And finally, that's how we show the final indices, which is that's what we have to find for this question. But how we get these U, V, and W? So you can see here U is the So yeah, it's a similar question. It's asking for finding like the indices for this direction in the hexagonal. So first you have to find the U and V and W, and that's how we do it. So U is gonna be, U is related to this A1 axis. V is related to A2, and W is related to this Z, kind of like a Z axis. So U is the difference between the starting point and the end point of that direction with respect to this A1 axis. Does that make sense? So the starting point, for example, here, it's 0 regarding all the directions, but the end point is going to be different. For example, the end point, which is shown by this right here. Well, if you want to find the location of the end point with respect to this axis, and if you project it, you get -1. So it's end up at -A actually. It's kind of hard to imagine, I know, but if you project that end point with respect to these axes, that's what you get. And you have to do like, you have to do the same thing with regarding to A2 and the Z-axis, and that's how you get U, V, and W. Is there any questions? Any feedback? So in other words, I can say like that. So for example, you are finding the coordination of points based on these three axes, right? So the starting point or the tail of this vector is going to be 0, 0, 0 because it's starting at the origin, right? At the end point, you have the coordinations here with respect to those three axes, right? So with respect to A1, it's going to be 0, which is kind of makes sense because this vector is in the A to Z plane, right? It's in this plane, which is perpendicular to this vector here, A1. So the endpoint coordinate for with respect to A1 is going to be 0. For A2, you get -A because it ends here. If you project that point to the A2 axis, you get -A. And how about Z? For Z, well, if you project that point until you cross the Z axis, it's going to be C over 2 because the whole height of this structure is C, and it's kind of like midpoint, so it's going to be C over 2. And the rest of it just simple math, and the n factor is just a factor. We multiply the final answer to get like integers or fractions. So it's the common factor between these three numbers. So, does anyone have any questions so far? So when you get these three numbers, finding these four indices is just simple math. Just have to do these things, and these four numbers are going to be your final answer. That's how we show. And again, we have to multiply by the common factor here to get integer numbers. That's why we just for example, in this case, we multiply everything by 3. And this is the example 3.9. We can take a closer look. This is pretty simple. In general, that's how we get like coordinates for direction. That's how we show a direction in hexagonal structure. And it's the same with your assignments. Repeat this process. To find Miller indices by similar lecture slides. So it's about planes. So far we talked about like points and vectors like directions. So this is about planes. So to find the Miller indices for a plane, what we do is, so if we find the cross section of that plane with all 3 axes, so for example here it crosses the x-axis at this point, so we find this coordinate and this coordinate, and that's the point it crosses the y-axis, right? So you find those coordinates, and what you do, for example, if we call it like, if we call here A, B, and C, then you take the reciprocal of those numbers, and it's going to be your Miller indices. textbook example, just wanted to show you how we find the variances. I believe you have it in your lecture slides as well. So first we find the intercepts between the plane and each axis, right? So for example, here in this example, it intercepts with the x-axis at this point, which we call it A, and intercepts with the z-axis at the point C, and it never intercepts with the axis Y. So we have A. That's how we show narrow intercepts with one axis. And we have A actual infinity times B and C, right? Yeah. And then we just have to take reciprocals from those, right? So we end up with, so we have 1 over A, 1 over infinity, and 1 over C. So these are fractions, right? Then we have to normalize it. So we times each fraction by the dimension of that axis. So if it's x-axis, we times it by A. So 1 over A times A becomes 1. And 1 over infinity times B, it becomes 0. And finally, we have 1 over C times C becomes 1. So that's how we find the Miller indices. This question is actually going backward. So here you have the Miller indices, or in this example, you have the Miller indices and trying to find the intercepts. So it's like a backward process. That's how we do it. So have any question about Miller indices? You know how to find the Miller indices? No question. So this, so this assignment, this should be easy.